We're back online. Okay. Make sure, do we have everything in the chat windows okay?
Yep.
Okay, like I said before we left, I'll just finish covering these last couple slides, and then it's going to be Q&A. So it's up to people here and online to ask us things that are not clear, or things that we can review again. All questions, because of course we speak quickly. We understand that, and because we know it well, or we think we know it well. So please ask us questions. We went through all this stuff about how the things you have to worry about if you change topography. So keep that close to your heart. If you're really doing something that is far from present-day Earth, write me and let me know so I can make sure that you're doing everything that you should, so that you don't waste weeks and weeks of your time doing things that look okay but really aren't. Okay. Let's talk about a few other things. Tom Clooney will talk about the calendar in much more detail tomorrow, and there's some details in the calendar here, but there's other things to consider in the model of importance for people that want to change different aspects. So there's, of course, the eccentricity and obliquity, and both of those are set in the Rundeck parameters section by these names. And they go just like you might think they go. Eccentricity is going from 0.00001, whatever, or 0, all the way up to whatever you can go. Although I don't know how high we've tried to go with eccentricity. Did we have this discussion, Chris, the other day about how high anybody's ever gone with eccentricity?
No, we were discussing about
we
had no clue.
Yeah. I've gone as high as 0.3. I haven't tried higher than that. Is anybody?
I've gone to like 0.5.
Crash.
It crashes above 0.3?
Constant, because I mean, part of the issue is when you get close, you're bombarding the planet with lots of
issues. When you're close, you're getting high insulation. Okay. But Stephanie, you said how high did you try to go?
Oh, I tried doing 0.5 at modern Earth insulation and it crashed.
And it crashed. Okay.
Yeah.
Well,
I wasn't surprised by that. But
well,
that might write that, but as Chris said, it might not be that.
It might be a Norway thing.
It might be.
it could have been the.
it might be the radiation.
Yeah.
Yeah, so if you move the planet out, then it might survive.
We don't know for a fact.
Yeah.
Yeah, we should. That's right. There's two things going on. The radiation, as we said before, is only valid for certain temperatures. So if you go outside the bounds, the model will crash. And sometimes the dynamics also friendly.
So is the issue there the rate of change for an eccentric orbit, or is it the maximum?
We don't know. We don't know the answer because I've only gone to 0.3 and I never had a problem.
Again, we should just try it with a more distant planet.
Yeah, we can. Yeah. It's one of those things we can
See whether it at least gets the orbit.
Yeah, until we hit the cold limit. If this planet has water. I mean,
or do it with a planet without water, just to see. Yeah, the question is whether the orbit itself is correct for high eccentricity or not. And we just don't know the answer to that yet. So the best thing to do would be to try it for a cold, dry planet, where even at very apps, not receiving that much sun.
Yeah, and there's also something called planet name, which I should use a different share for that. I want to talk about this window. Oops, that's my bad typo. Typing. I have to minimize this thing. Okay. I don't know why the screen's blinking. Good question. Okay. So there is something we call planet name, but really there's this in the preprocessors options section. Let's say you want to change the mass of your planet, or you change atmospheric constituents. So the mass of the air in your planet is not the mass of the air on Earth, because air on Earth is, so much nitrogen, so much oxygen, et cetera, et cetera. But let's say you want to go pure CO2, you have to change the molecular weight of the air. That's in another file, which we'll get to later, but you have to first define what you want to call that planet in that file, which I'll show you in a moment. And so you have to use this thing called define planet params, and you give give it some name. Here I've got not Earth. So we'll go to the file where it tells you what that is. Model shared directory. So in your model directory shared, there's a file called planet params mod.f90. Go down here. You see, here is where you define a new planet. In this case, it's not Earth, but actually it is Earth in this case. It's just a template. So it has Earth gravity, radius, molecular weight of the air, the CP over CP, the specific heat at constant volume over constant, constant pressure over constant volume. That's SRAT. What the surface pressure is, what your pressure at the top of the atmosphere is.
No, this is where the sigma layers
sigma layers
become constant, but this is relaxed in Planet 2.0 because we have a smoother transition, but still we need it. It is something like around the tropopause.
Yeah. And then what your atmosphere is made out of. PN2, what's the partial pressure of PN2, PO2, and P argon in this case. And there are others you can add here at the top. You can add pH2 also if you have an H2 dominant atmosphere. We do have spectral files that allow H2 as well. So if you go down here to Mars, for example, we have a like Mars entry. You can see here we've changed the gravity, we've changed the radius, we've changed the molecular weight of the air to be pure CO2 in this case. We changed the CP over CP value, the SRAT, and of course these pressure functions. And then of course, in this case, it's pure CO2, so there's no nitrogen, there's no oxygen, and there's no argon. And if you don't define pH2, by default it's 0. It's set at the top of the model. So if you want to do different kinds of atmospheres, you have to make sure that you make an entry in this planet params _ mod.f90 file, which is located in this model shared directory. And again, you have to call it at the top of this file of your run deck. So here you see define planet params not Earth. Then we have another thing here, planet name. Oh, is it planet capital name? Okay.
There's no planets only. There are not many cases.
No. Find him here because this is a not Earth. This planet name that
comes
right after
in two places, but the second probably is not very important because it's kind of like it's not really for diagnostics.
Yeah.
It's
right above electricity on top.
yeah, it should be somewhere.
Yeah, but not in this.
They don't have any
parameters.
All right, well, those are not so important. The important thing is this planet params, so that if you're going to run with a different kind of atmosphere, make sure you make an entry in that planet params _ mod.f90 file, and make sure you put a new name here in the planet params. Be careful that you don't take another name that's already there. I don't know what will happen.
It will not compile.
It will not compile. There's the answer. Seems like somebody's tried that already.
No, it's based on the structure of the file.
Okay, good. All right, let's go back to our slides.
If you have the PS Mars run deck,
Yeah,
that
should we
has
look
the
at
planet
that?
name. Yeah.
Let's see.
Yeah, planet
you can-
name.
Make run deck.
I think it's just kind of diagnostic thing. So it will not change how the model is computed, but some names somewhere will be as planet name.
Yeah.
Because the CPP statement, that's what is important to us, I think.
Yes.
All the properties.
The planet name, if you search by application, I think.
So it's capital.
Lower
No,
planet,
lower-
capital M.
Capital M.
There it is.
There
Yeah.
you go.
It's not critical, it's that preprocessor.
Actually, it could be used by calendar. I'm not sure because I think it is passed to calendar. But you specify everything explicitly. So.
Yeah, it just gives it a tag.
Yeah.
I don't think it's necessary. Okay, well, we can look quickly at the calendar. Let me go back to my terminal window. So there are some calendar things. There's this sidereal orbital period that's in the slide, which people online and hopefully here are looking at. So period and quantized year length. Those will not be defined for the other planets, but let's look at this PS Mars run deck. So, as I said, Tom Clooney will talk about this tomorrow morning quickly, but I just thought I'd show an example where these are defined. So this is for modern day Mars, where we know things like, of course, the eccentricity and the obliquity are set appropriately. The longitude of periapsis, we know for Mars. If you don't know the longitude of periapsis is for your world, well, and you don't define this, it will use Earth's longitude of periapsis. Anything not defined will use the Earth default. Sidereal orbital period is going to be in seconds, and the sidereal rotation period. So we don't use solar length of days, we use sidereal days because some of us started off life as astronomers or were associated with such beings.
So then the model calculates the appropriate solar data.
Yes, it does. It does calculate it. And you can see that in the output. One thing I think we haven't mentioned is that when the model runs, it does output
The output
model.
is another slide.
Yeah. Is it in the,
Yeah, it's down
put it
below.
in tomorrow?
I think not.
Next slide? No.
One more. One more.
No.
Here.
Oh, okay. So we'll get to that later. All right, I apologize. And then there are these things like quantized, there's this thing called quantized year length, which is a way, it's something you should use when you're using totally locked worlds, to guarantee that the planet stays fixed, the substellar point stays fixed for a given longitude.
It has a caveat when you use it. So essentially what quantized year length means is that if after the calculations of the orbit, it says that for a full orbit around the star, you need like 25.7 days, it will make it 26, but to the expense of changing the model time step. So if you want to calculate the model time step, you want to use the model time step for some reason, and you are using this quantized year length, you need to go in the output and check what is the actual time step that has calculated via the calendar based on what you provided.
We'll talk about that. Yeah. Now, we did talk a little bit about this GHG file, and we kind of mentioned in passing, I can go back to this slide just to show again. GHG file, which we showed for 1850. We had a discussion about using 1850 in the greenhouse gases file for abundances of greenhouse gases like CO2, N2O, things like that. And then we did mention that there's also these other factors you can multiply by, O2x, CO2x, actually N2OX, etc. So this can be a little bit confusing. So you have to be very careful when you're using these multiplicative factors in the run deck as parameters and the GHG file. Different people have different philosophies about how they like to do this. And I'm not going to go into those philosophies because it could take a long time to sort out. But for example, let's say that you're using a GHG file and you've set your CO2 ppm to 400 in that GHG file. You want to use 400 ppm CO2, but then you change your mind. I want to run 800 ppm CO2. I can go into my run deck and change the CO2x to 2. So it will take the value from the GHG file and multiply it by a factor of 2. So you can do something like that. I personally don't like to do things like that because I find it confusing. Some people like to use one GHG file for all the runs and then play with these multiplicative factors. I personally find that it can be confusing. So I prefer to create a new GHG file for each world with different atmospheric constituents. You don't have to do it that way, but that's just the way I do it. So I set my GHG quantities in that GHG file, which is an input file in your parameter section of your, or input section of your run deck. And then I leave these CO2x things set to 1. I don't touch them. The only time I play with these is, for example, for things that I definitely want to zero out, which are not defined in the GHG file, and that would be the one first listed here, O2X. So that's not defined there. That's hard-coded into the model in the radiation.f file. And rather than play around with that, so I want to take oxygen out of my model most of the times, I just set this to 0. If you set O2X to 0, it zeroes out the oxygen in the model. Okay. So those are just things to keep in mind. There are different philosophies about how to handle the greenhouse gases and these other atmospheric constituents. Just be careful when you do it.
For people to understand why it's so complicated, it's basically like comes again from the Earth GCM, when GHG file is supposed to set whatever is observed, and that's usually how people prefer to keep this GHG file, these observations. And if you want to do some weird experiments when you want to deviate from those observations, then you specify those multipliers in the run deck. So that's why historically it works like that. For like planetary runs, maybe some people prefer to set everything in GHG file to 1, and then in your run deck you just specify the real number that you want to do, other way around. Same, but because in that case you don't have to create 100 of GHG files, you just have 1, and everything is in your run deck.
Yeah. So it's just different philosophies. You decide what works best for you. Okay. And the only other thing to change in these run decks with respect to other worlds is how much insulation you want to give the planet, and that's set by planet_S0 when you're using the Socrates radiation. And there you just give it how many watts per meter square the planet is receiving. So if you want modern day Earth, it's 1371. And you just, if you actually want that, you can comment it out. That will be the default value. But if you want to increase it, that's where you increase it. So we let you set directly what the incident radiation should be. 1361, sorry, yeah. As soon as it came out, I realized I was off back then. 1361 is what we call the solar constant, although as Judith Lean points out, the solar constant is not a constant.
Yeah. Even on short time scale.
Yeah, even on short time scale.
The 11-year solar cycle.
But yeah, 1361 is the default. You can set, if you want to set your insulation, that's where you do it. The planet_S0 is where you set it.
Is there a time variable solar insolation option?
Is there? No.
Okay.
Oh yeah. Oh yeah. I don't know how to do it, but I mean, when we run the Earth model, we have to have time varying insulation to capture not only the 11-year solar cycle, but longer term assumed, not really observed, but assumed secular changes due to sunspot.
Okay, sorry, Maggie. The answer is I don't know.
Like that. So you can do that.
Yeah. I don't know how you do it though.
Yeah.
But actually, one more thing about this.
But we have people in this building who know how to do it for somebody who actually.
Yeah, we have people.
About installation, you can also specify the distance from the star, and we usually use it only for Earth. So basically, we use it only for Mars on deck.
Yeah. Some of us don't recommend doing that. We prefer it's easier just to use one.
It is important to remember that not to use both at the same time.
Don't use both at the same time, meaning just use one. Okay, anyway. Some philosophical discussions about that. Okay, now, this model loves to crash, as you will discover when you start changing things and nothing works. So we have a Google Doc with the most commonly known crash solutions, basically, so solutions to crashes. It will not solve all of your troubles, and it definitely won't solve your troubles if what you're using is wrong from the start, because, well, that's another issue. But the most common sorts of crashes are documented here, and we have tried to reply to them the best of our knowledge. So you can go to this link and see.
Is that linked off the documentation page?
It should be. I don't know. Remember if it was set there or not. Maybe not.
Because I know from experience, if you can't find it, just email Mike and he'll email it to you directly. Have you looked at this file?
So everybody has access to this presentation.
Yeah.
So it's there.
Their link.
What?
What?
Yeah.
I can use it.
Really?
Okay,
For me,
it's just Jade.
the file doesn't exist.
Maybe because it's got a carriage wrap, carriage turn.
No,
maybe you
Maybe
copy,
if I
paste.
copy paste.
copy paste. You tried to type that in. You're very good.
No, I think that.
No, but there's a current user in there, and that might add the space.
At least one person here says this link works. The other one says it doesn't. Okay. So now the tricky parts, output and post-processing. So as I was saying before, as your model runs, in the directory in which your netcdf output is located, that symbolic link from the dex directory to the run ID, there will be a file with the name of the run ID, .prt, and that's where the model spits out all of the runtime messages that it thinks are necessary for you to know about. And that's where you will usually find the message that your model has crashed for some reason, or is just running along happily. So that PRT file, we can actually take a look at the one for the model you should have run. I should have it here. Let's take a look. So here, again, in that dex directory, you can see the following thing. So if I go to the E1SOM40 test, CD there, from my dex directory, you can see it's still in there, even though I'm symbolically linked to my huge space directory. If I ls in there, there's a P1SOM40 test.prt. We can take a look at that file, and it's got useful things in here that you might want to check. Like, let's say you have your graduate student decide to run the model, and you want to make sure that they actually set the eccentricity of liquidy correctly. You can check it. Or if your graduate students want to make sure that you have set the eccentricity of liquidy correctly, it's spit out here, along with the longitude of periapsis. And it also spits out what the calendar is for the particular setup that you've asked for. In this case, it's just an Earth calendar with normal length of months and like that. It also includes Johannes Kepler's birthday. Apparently, it used to have Jim Hansen's birthday, but that was considered PII, and we had to take it out. Jim Hansen's the former director of this place and a climate denier. I'm joking. The complete opposite.
The exact opposite, yeah.
I had to put it. There's all kinds of stuff in here. Most of it is not so interesting. But you know, here's one thing that you can notice. Minimum J with some motion. It's set to 4. Good thing I'm not running an exoplanet here, because it really should say 1. So that's that little trick I told you to where you can edit the source file. Then I can go down here and I can see what my atmospheric constituents are from that GHG file. It prints out the first few columns from that file to make sure that you're using the GHG file you think you're using. A few other things of interest. Nice to see. All kinds of stuff from your run deck show up in here. And then, of course, all the parameters you set in your run deck are here. So you can catch your own typos, in theory. Which spectral files you used. We'll talk about those a bit later.
The I file log the similar information?
No, the I file contains the information you've given the model.
Okay.
This contains the information the model actually saw.
So there might be. So if you have a typo in the the model will not be able to figure it out, and then it will give you the default.
I see.
And actually, it's important to look at the end of this file. It will show you which parameters from the run deck were not used.
Yeah, I've just gone to the bottom. You can see.
Yeah. So you see,
These
like,
2 warnings, you see?
yeah. So these are 2 legal warnings. These things are really not used, but if you misspell something and you think that you are using it, here it will show up as unused parameter.
Like if you misspell obliquity.
If you make 0 mistakes with the I file and the PRT file correspond exactly to each other.
Yeah.
So,
The entries in each that
they should be.
equal, they should be exactly the same. Yeah.
And
This is where you can find.
when you say not used, is that what you're saying, where it would defer to the default?
No, not used means that you define something in the run deck, and then the model, during its runtime, never used that value because nobody claimed it.
Never requested.
So it was never requested from the model.
Name.
It could be that an old module was requesting it, but we never took it out of the run deck. It's still there, and so the model says, nobody wanted this. I wanted you to let you know that it's not being used.
For example, the sub-DD one, this is there, and the model only requested under specific circumstances, and the default case is not to request it. But nobody deletes it because it's useful to be there, because frequently it's used.
We may talk about sub-DD later.
Yeah, and the first line is exactly what somebody else mentioned, that it was from the, in the old run deck it was necessary, but now it's not, but it's still there. Which
Oh, yeah, exactly. Exactly. And there are other things in here. There are some tables of, if I can look for, like if you quickly want to know things about your model, you can look at these budget tables, we call them. In this case, I'm looking at the global budget. That's what I looked for with, in parentheses, global. And it'll give you what those values are for the model for that given month. So you can see here, budgets global from 1949 December 1 to 1950 January 1st. So that's 1 month of December for the model, and it will tell you all kinds of things, most of which won't mean much to you, but the first items on the left are the description. So INCSW is the incident solar radiation that the planet sees, the global value, a northern hemisphere value, and a southern hemisphere value. To get your planet _0 number back out, you would multiply this number by 4. If you go down a little farther, other things that might be of interest are things like T-surf. That should be down here. All kinds of stuff. T-surf, here you go. It's at 122.9, but for again, one of these legacy reasons, it's this value times 0.1, so 0.2 is the global value for the surface temperature in this case. So these are quick and dirty ways to check if your model's running okay. Rather than opening your NetCDF file and plotting it in Panoply, you can just look at the budget pages. And we have people in the building, I would say older gentlemen in the building, when you ask them for help to look at a run deck, these are the pages they want to look at. You start saying, oh, I can show you in Panoply. No, I want to see the budget pages.
Show me the PRT file.
Show me your PRT file. And they can.
ASCII maps in it. I was watching it going by and I saw maps of West America there.
And as I found out on Friday, I think, these have appeared in papers in the 70s and 80s.
Oh, wow.
I don't know if I have a map in here. No,
I am too young for that.
I mean, this goes back to the days in the 1970s, 80s when the output of the GCM run was a paper output. And what you're seeing up there is what came out of the printer.
Yeah.
So,
It's pretty cool to see the maps go by.
it's never changed. I mean, fortunately, we have the next CDF. That's what these things are. It's the old school.
Yeah, some of them look more like maps than others.
Your key file can be
there.
After the reference to punch cards, nothing surprises me anymore.
Greenland's line.
So a little bit more about the output. Again, if you're looking at the slides here, as the output. Okay, since we're an Earth-based model, we output by default in months. Okay, so we output 12 months per year, and you can see here I actually did run this model for the first month. Although we only asked you to run the first hour, I went ahead and ran the first month, and you can see the first month it created was December 1949. It generates a file called an ACC file, .acc, and then it has the run deck name, P1SOM40_test. So that was the first month generated. If you look at my I file, you can see down here that I set year end to 1950, month E1, date E2. So this ran 1 month of the model.
And the day.
And the day, yes.
Actually, one important thing I wanted to mention about PRT file and sort of different is budget tables. If you want to run your model to equilibrium, sometimes it's very useful to look at certain numbers just because, like, for example, we want to see the energy flux like at the top of the atmosphere. So instead of looking through a lot of NetCDF files and trying to integrate those together, those tables can show you exact numbers that you want to look at to see if the model is in equilibrium.
Tomorrow we'll talk about equilibrium in some detail, what it means for the model to be in equilibrium. So don't worry too much about that now. Igor can more about it then. So So anyway, as the model moves forward, it's going to generate monthly output. So December 1949, if I had let it go forward, it would have next generated January 1950, February 1950, on and on and on the model will go. Those numbers, again, that 1950 or 1949 are all based on this. So typically when I run an exoplanet scenario, I set this to 1, 0001, and I might set this to, say, 100 if I'm going to run 100 years. Or if I'm going to run 1,000 years, I can set this to 1,000. Or if I'm going to run 10,000 years, I can actually do that as well. So all those are possible options in the model.
One thing that is kind of important for the Earth model is that our default restart file for Earth is a December 1st file, and that's why we typically start on December 1st.
I'm getting there.
Sorry about that. And then the other thing is that the ACC file that is saved is always saved at the end of the month. The moment the month changes, it's saved. So if you run the model for a full month, you will get it. If you run the model for the last 3 days of the month, you will get it. If you run the model for the first 25 days of the month, you will not get it. You need to change month in the model to get the ACC file. And then it will contain that many days as the month that has just finished.
Yes.
Does the planet version by default use equal length months?
No.
You can see that
here. So that will be covered by the Clooney tomorrow.
Got it.
But in short, we take the Earth calendar.
This is the Earth calendar.
And with no leap years. And if we have a planet with less or more than 365 days, it adjusts that uniformly. So February will always be the shortest month.
Okay.
And never with a leap year. But Tom will cover that.
Tom will hopefully cover that. Now you might ask, like I said before, why would I ever set this to 10,000 when, or let's say, well, not 100,000, but let's say 20,000, when I told you at the very beginning of this tutorial that we don't run the model for this long because it takes too long. But of course, there are cases where we want to run things around M dwarfs where a year is extremely short. It might just be a few days. And so each one of these years is one of those orbits. So year really means orbit in this model. And we have I ran Proxima Centauri, I think 15,000 orbits in some cases to get the model into equilibrium, which again we'll talk about a bit tomorrow. So while it might seem that this is a crazy number, there might be reasons why you want to set it higher.
And it only goes up to 6 digits.
Yes, it only goes up to 6. You can only go up to 999,000 orbits.
Is there a reason you're setting it to 0001 instead of just 0?
Just nice format.
Nice format. You can set it to 0.
No, you can't. 0 doesn't work.
Zero doesn't work?
No.
Oh, I've never done it.
You have to start with 1.
Okay, someone knows for a fact that you cannot set it with 0.
I
See,
wonder
that's what
why.
happens when you let people use your model. They do things that you never even thought to do.
Zero, probably just.
So you are teaching next year, right?
Exactly. Next year, Stephanie's running this tutorial.
No, it doesn't even start. It just gets done.
Okay, now, there are restart files that the model generates every, what is it, the Fort 1 that generated?
So there are 2 types of restart files.
Oh, yeah, let's talk about the Fort 1 and Fort 2 first.
You want to speak about those first?
Yes.
Okay.
And then we'll get to the R side.
So there are restart files that we frequently call them checkpoint files. And they are saved frequently as defined in the run deck by the variable named ndisk. So you set ndisk to equal something. Usually there is no usually really. So here ndisk is 480 in the middle of the screen.
That's the default value.
The default is 960, I think.
Okay, but it's set to 480 and I think on every run.
I think it's too early for the M resolution.
Yeah.
So anyway, that means every how many time steps the model will save a checkpoint file just in case something goes wrong. And when it reaches that time step, it saves a file that is called fourth.1, and then it saves a file called fourth.2 the next time, and then it alternates.
Overwrites the previous.
Yeah. So you always have one file that is ready to go, and you don't override it continuously, so that if something goes wrong, the moment you write the file, you lose everything. So the moment the model starts, saves the initial conditions in fourth.1. So essentially, it is before even any time step. And then after 480, saves the 4.2, and then starts alternating. And if something really goes wrong, what you can do is that you can, if the model crashes and you have no idea what happened and you just restart it, it will automatically search those two files. It will pick the one with the most recent date in the file, and then it will restart from that. So in the worst case, you are going to lose 480 time steps, which is no big deal.
But there are cases where the latest fort file has been corrupted. Let's say the disk crashes as it's writing out the fort file, or your model crashes while it's writing out the fort file. So you might want to get the one that's a little older. I've had cases where both fort files were corrupted for some very strange reasons I never could sort out. And so we have a backup file, which will...
If only one was corrupted, you can override the older one to the newer one. You have, so fort 1 and 2 will be identical, and the model will figure it out. But if both are corrupted...
Yeah, if both are corrupted, then you have to use a full checkpoint restart file, and that's what's called an RSF file. And you can see in your directory, if you ran the model correctly, you get an RSF file. So you see one here called 1 January 1950 RSF, and then again, your run ID, P1SOM40_test. So that's your full checkpoint restart file. The model will write these out at intervals that you decide. I believe it should be, do we have a default set for this?
Planet 2.0 is 120.
120, I don't know what it is.
So every 10 years.
Planet 1.0.
Planet 1.0, I don't remember.
There is a rundeck parameter called KRSF, which will write these files out every KRSF months, as we call it. So let's say you want to write every 120 months, it'll write out one of these checkpoint restart files every month. You might ask me, why don't I just write one out every month? Well, because these files are huge. It's a complete snapshot of the model, so you don't want to write these things out every month. So we let you decide for your run how often you want to write these files out.
It's like backing up your computer.
Yes.
How much work are you affording to lose if something goes really, really wrong?
Yeah. So that's what you have to calculate. Are you willing to run the model over again for a day, a week, or a month, or 1 hour? You have to decide that. So that's up to you. So that will be this KRSF parameter, which is not in this, which we didn't set in these runbacks. But now,
mostly you want this files actually for physics reasons rather than for technical failures, because for technical failures, fort 1 and fort 2 nearly always work.
I've had cases where they did not work. Okay.
Yeah, it's really,
I know that
it's really
it has happened.
But what sometimes happens that your model crashes and you realize that it basically started to divert from a reasonable path somewhere else because something wasn't set properly. So you cannot just restart the model from previous time step. You have to go like a few years maybe or a few months back. And that's when these restart files are really helpful, that you don't have to restart your entire run from the beginning. You can just find a restart file with several months.
So you're saying you can use this to restart your model and change some parameters in the model, and then allow the model to go forward from there. That's the point. That's the other extremely useful thing about these full checkpoint restart files. And to use those, I don't think we mentioned it here, but it's fairly straightforward. So I think it's actually written in here. Yeah. So if you want to use a checkpoint restart file, let's say you want to go back a few hundred years, you enter it as the AIC file. You can see there's an example sitting here where it says AIC equals 1 January 1961, and here's the RSF file for that.
This is just an ancient example.
I know.
It's not even NetCDF.
Yes, exactly. But anyway, you would comment out that line and put your RSF file that you want to restart from there. Then you have to go down to the bottom of the file, and here's where you change that iStart to 8, so that you tell the model when it restarts, I want to restart from this checkpoint restart file in the AIC.
Actually, depends what you want to do. Most likely, you would want, if you want just to continue your current run, you will set it to 9.
If you want to override your previous result. If you
No, you don't override it, you just continue. But
yeah, but it will override from that point on.
basically, the technical difference between 8 and 9 is that 9 just reads the restart file and doesn't do anything else. iStart equal to 8 also reinitializes certain things in the model. So the continuation will not be identical as if you were just running the model continuously. That's basically the only reason, the only difference. So it's up to you to decide if you really want to have like complete reproducibility, then you should start to 9.
But you have to take advantage of this in the middle of a run, you have to recompile the model. So you have to do the make setup, but do not run the cold restart if you want to start from where you began before. Otherwise, you could start back from.
You usually cold restart file with 8 and 9.
Well, do you have to use it? I thought you don't have to use it.
Yeah, otherwise, it would always start from port 1.
Oh, we'll start from, oh, sorry, no, you're right. So you do have to start the cold restart.
Yeah, so certain worker is needed, like you choose which one, 8 or 9 to use, and also for year I and month I, you have to set those values from that restart file that you are using.
Yeah, if you want, if you want to start, okay, I've done it a different way, but yes, that's right.
If you want just to continue,
you can do it Igor's way. I have another way to do it, but that's fine. We can do it Igor's.
Well,
we all have our own.
There are many ways to do the same thing.
Exactly.
That is something that you will notice in.
Yes. My method also works, but
well, it's important when you basically use a restart file to set your calendar properly, because otherwise you might override your existing file.
That's what I was saying.
Yeah, well, that's because you were not setting the.
Yeah. Okay. Well, anyway, that's what this checkpoint restart file is all about.
Michael.
Yeah.
Do these checkpoint restart files carry information about any kinds of momentum within the system, so how things are moving as opposed to a static snapshot? So I guess the question is,
it will capture the wind speeds in the model. If that's what you mean?
Okay, so they're going to be fundamentally different from the initialization conditions, which would be static.
Oh yeah. And in fact,
includes the momentum.
In fact, you can even use these for a completely new model run. Let's say that you've run this model for thousands of years to get into equilibrium because you change the solar insolation by 50%. You can then take one of these checkpoint restart files and start another model run from that at that higher insolation, and it will decrease the time it takes it to get to equilibrium by a large amount without having to change all of your other input files and all your boundary condition files.
Even better is something that we have used, which is probably very relevant for your interest. We wanted to explore volcanic eruptions that happen at one point in time, and we wanted to explore really many of them. So we ran one model to equilibrium and started from that checkpoint file, and when it allowed volcanoes to go off at different points, locations, and places, and everything was already spun up because we had the restart file.
So similarly, the 1850 baseline model, is that actually a snapshot of 1850, or is it an equilibrium solution that carries those velocity and momentum terms, if you would specify that as the beginning point for an Earth model?
It is an instantaneous state of the model.
But at equilibrium for conditions.
If you saved it if you stopped it at equilibrium, yes. Otherwise, it will be wherever it is. And the equilibrium doesn't mean anything really. In equilibrium is a state averaged over a long period of time. So it might be, so if you have to run the model for 100 years to reach equilibrium, and then you save year 100, it doesn't mean that time slice is the equilibrium condition. It is just one of the data points that, if you average over, will be in equilibrium. So it might be fluctuating up and down. I mean, we'll have a slide.
We will talk about this.
There is a slide later that shows the equilibrium state.
We'll talk about equilibrium tomorrow.
Basically, the idea behind restart files is that they are pretty much core dumps. So the idea is that writing a restart file and then restarting from it is the same thing as if you just were running the model continuously without any stops. So the model shouldn't feel it, and we check it that actually it's bitwise reproducible in that sense. So that's basically how you should treat it. So you think about it as if you were already running the model like for 1,000 years, and then you start to do certain experiments. But in reality, you just stopped it, wrote the restart file, and then restarted from it.
And hence those files are very large because they are capturing, it's a core dump.
It seems like it's much larger than the initialization file if it carries that other information.
They're bigger than initialization file, but they're not terribly large. The problem is that when you write them often, then there are a lot of them, and that takes a lot of space. But actually, they are smaller than checkpoint files, because checkpoint files contain also diagnostics, which are reinitialized every month, so you don't need to save those in the restart file.
Okay, so just a couple more things. We'll take a quick break here. So as you saw, there was this December 1949.acc runid.nc file name. So those files contain your model output, but they're not useful to look at themselves per se. You have to generate diagnostic files from the ACC file. So we have a command which you built, all of you should have built, called scale ACC, and you can use scale AC to generate what we call AIJ files or all kinds of different files, which we'll talk in a little bit more detail tomorrow, hopefully, about how you generate specific diagnostic output files for the specific physics you're interested in looking in. Another file, another utility that you should have compiled is another one called sum files. So often we don't want to look at a single month. We might want to look at a 10-year average, kind of like we were just talking a bit, because I might want to know what the last 10 years of the model run is, because that's an equilibrium period for the model. So you would use sum files, and you can sum files. You can sum any number of files you want, but in general, we usually sum, say, the last 10 years if we want to look at specific diagnostics. And then you would sum files, the ACC files, and then you would scale ACC, the combined file. And the sum files will try to generate a file name that is consistent or makes some sense out of what you gave it. So if you generated 100 years, it will tell you what 100 years that it generated in the file name. It's pretty clever.
Yeah, you also can make sums for seasonal.
Yes.
For seasonal periods, and it also will figure out all this, like June, July, August, or like December, January, February.
Yeah.
If you give it something weird, I don't know what happens. Usually, you never do. But it probably will still.
If you do January, March, September, who knows what we'll do? Yeah.
It will probably produce correct files, but with some strange name.
Yes.
If you combine June, July, August, say of 1950, it'll call it JJA1950.acc. That'll be the file name you get out, for example.
Just to go back to the RSF files, I'm checking the Planet 2.0 RSF file sizes. So the resolutions that we're talking here, the 4x5, 40 layers. Every RSF file is 74 megabytes. If you go to the fine resolution, which is 2x2.5, every RSF file is 287 megabytes. And if you put the coupled ocean in the fine resolution model, it is 684 megabytes. So if you're doing a 10,000 a year simulation, you need to be careful. Yeah.
Yes. We'll need petabytes. That's the way we're going. Yeah. I've never used diff report. Do one of you want to talk about it?
So yeah, diff report is a very fun tool that we have developed in-house, and which essentially makes a diff between two NetCDF files and reports differences. Okay, the first question that comes in mind if you know NCO is why not use NCDiff? And the question is that NCDiff will check bitwise the NetCDF files, and if the metadata are different, it will report differences. And even more than that, it will just tell you, hey, these are different. But diff report actually ignores metadata completely and goes into the variables, and it checks every individual data point and tells you, okay, these variables are different, and the maximum and minimum differences are these, both in absolute and relative terms. So you can figure out exactly which variables are different. And also, if the two files are slightly different, so for example, one has less variables than the other, NCDF will tell you these are different, of course, because they have different number of variables inside. But diffreport will tell you, okay, everything is identical in the data point, except that those 5 variables are missing from one of the 2 files. So it's a really smart way to do it. So if you're doing development or debugging of, especially in cases that you know that the model should not change answers, it is extremely useful. For example, you want to understand what the model is doing in some part of the physics. Okay, so you go in there and you find some code from the 1970s that you cannot really follow, and it's easier for you to simply restructure the code to make it readable for you, and then make sure that everything is the same. So you run the model before you make your changes, then you restructure everything, you run the model again, and you expect exactly the same answer. So you go there, you say diffreport the ACC file of one and the ACC file of the other, diffreport should report nothing, which means, okay, you restructured it, and everything is still the same as in terms of results. So in real life, it's useful for developing rather than actual production, but it is an extremely useful tool that if you're using NetDF files of any kind, it can be useful beyond ROCKE-3D.
So do you just do diffreport name 1, name 2?
Yeah, yep.
And it's based
ACC,
into ROCKE?
name 1,
Oh,
name 2, yeah,
okay.
from your output.
Great, thank you, Kostas. I think I already mentioned Panoply, and there is another NCDF viewer that people use, Igor particularly, called NCView, and Kostas, okay.
I'm using different viewers, which
We use a viewer.
Oh, now you're using a
you
viewer.
mentioned it here. Which
Okay.
I wrote myself.
ASCII maps?
Okay, so just quickly, I think we should take a break because it's been an hour. And we'll take a 10-minute break and then we'll come back and I'll quickly talk about these output diagnostics I put up here, just very quickly. And then we'll take your questions and answers until we quit. So we'll take a 10-minute break and come back. So get a coffee, whatever you'd like to do. And we'll come back. So I'll mute the system while we're going to take our break.